You've already seen in a previous video that a set of so-called basis vectors can be combined to generate a new vector by means of linear combination. It's just a matter of scaling the basis vectors with appropriate coefficients, then adding the resulting vectors together. You might want to review the concept of linear combination before you continue. In this video, you will learn how to express a given vector as a linear combination of a set of given basis vectors. In other words, you'll learn how to determine the coefficients that were used to calculate the linear combination. For example, suppose that vector w is a linear combination of the basis vectors u and v. Recall that a linear combination of two vectors can be calculated like this, where x and y are the scalar coefficients being applied to the basis vectors. Our objective then is to determine the values of x and y. That is, we want to find out exactly what w is composed of. We want to decompose it. If we can find a pair of coefficients that do the job, then we've discovered whether or not w is indeed a possible linear combination of u and v. To put that another way, if a suitable pair of coefficients exist, then we know that w is within the span of u and v. You can probably see at a glance that w is a linear combination of u and v. But what linear combination is it? There's more than one way to find out. In a later video, you'll see how to determine the coefficients using matrices. In this video, you'll see how to determine the coefficients using some basic algebra. We can rewrite this expression more explicitly like this, because each scalar is applied to both components of the vector. Now, we'll remove the square brackets and rewrite again as two separate equations in regular algebraic form. We now have two separate but related equations with two unknowns. You may well have come across this sort of problem in school. In regular algebra, we call these simultaneous equations. In linear algebra, we refer to them as a system of linear equations. The variables x and y can be found using a process called elimination. First, multiply everything in one of the equations by a number that makes the term containing one of the variables identical to the corresponding term in the other equation. In this example, multiplying everything in the first equation by 2 will give us the term 2x. The x term is now identical in both equations. Now, subtract one equation from the other. Subtracting the second equation from the first eliminates the variable x altogether. And with a little rearrangement, we can determine the value of y. The value of y can now be substituted into either one of the original equations to determine the value of x. Hence, x equals 3 and y equals 2. We can check if these values are correct by calculating a linear combination of u and v with these coefficients. When we scale u by 3 and we scale v by 2, then add the resulting vectors together, we get w as expected. Here's another example. We want to know if vector L is a linear combination of the vectors a and b, and if so, what are the coefficients? What are the values of x and y? Notice that vector b has negative components. That shouldn't make any difference here. We can take the same approach. Start by rewriting the information we have as a system of linear equations. We are now looking for matching terms that we can eliminate. Multiplying the second equation by 2 throughout gives us 4x in both equations. Now subtract one equation from the other. It doesn't actually matter which one you subtract from the other. Whichever method makes the calculations easiest is perhaps the best option. Subtracting negative values from negative values requires extra care. In this example, we find that 5 times y is equal to 12.5, which means that the value of y is 2.5. Substituting this back into the first equation gives a value of 2 for x. Hence, L is indeed a linear combination of A and B. By the way, there are several ways you could approach this problem using the same algebraic technique. For example, you could make the y term identical in both equations by multiplying the first equation by 4 and the second by 3. You can then proceed to eliminate y and determine the value of x first. Ultimately, any path that leads to the correct result is fine, but the path of least resistance is probably the best. Now, consider this example. We want to know if Q is a linear combination of C and D. In a previous video, you learned that any linear combination of two collinear vectors must also be collinear with them. Well, you can see at a glance that C and D are on the same line, and therefore Q is not in their span. Nevertheless, let's attempt to find a pair of coefficients algebraically. This is the system of linear equations we're attempting to solve. We can multiply the second equation by 2 throughout, with the intention of eliminating the x term. But we've inadvertently eliminated the y term as well. This equation has no solution, and if you experiment with other collinear vectors, you're going to run into the same problem. The same method can be applied in three-dimensional vector space, or any other number of dimensions for that matter. Here we have vectors A, B and C, and we want to know what linear combination W is of these three, or indeed if W is a linear combination of these three at all. This time we have a system of 3 linear equations with 3 unknowns, x, y and z. Let's number them 1, 2 and 3 so we can see what's going on more easily. To solve this system, we need to choose 2 pairs of 2 equations and eliminate the same variable from both pairs. For example, to begin with, we'll select the second and the first equations and multiply the second equation by 3 throughout. This allows us to eliminate the z term by subtraction. Now we'll select the second and third equations and multiply the second by 2 throughout, which again allows us to eliminate the z term. We now have a new system of 2 linear equations with only 2 unknowns. Conveniently in this example, we're in a position to eliminate the matching x terms immediately, and we quickly discover that y is equal to 2. Substituting y into either equation of the 2-equation system gives us the value of 1 for x. And finally, we can substitute x and y into any one of the original 3 equations, and we find that z is equal to 3. W is indeed a linear combination of A, B and C. Now let's take a look at an example of how vector decomposition might be applied in the real world. It might not be immediately obvious why this is an application of vector decomposition, but keep watching and you'll soon see. This is Beatrix. She has £30 of birthday money to spend. Beatrix wants to buy some cake and some lemonade. The price of cake is £2 per slice. It's good cake. The price of lemonade is £3 per litre. It's pretty good lemonade too. Beatrix has worked out that she can afford to buy 15 slices of cake but no lemonade. Or she can buy 10 litres of lemonade but no cake. Ideally, she wants some of each. She reckons that if she buys 3 slices of cake, it will cost £6, leaving £24 for lemonade. That's 8 litres of lemonade. She's also spotted an alternative. She could have 6 slices of cake, which would cost £12, leaving £18 for lemonade, which will buy 6 litres. Beatrix is pretty good at mathematics, so she's written this equation to help solve her dilemma, where 30 is the amount of money she has, X is the amount of cake and Y is the amount of lemonade. For example, 30 equals 2 times 6 plus 3 times 6. Or 30 equals 2 times 3 plus 3 times 8. In fact, if the shopkeeper is prepared to split a slice of cake, then she could spend half of her money on cake and half of it on lemonade. That's 7.5 slices of cake and 5 litres of lemonade. Furthermore, if he'll split a litre of lemonade, the possibilities suddenly become endless. Beatrix is very conscious of the impact that all of this sugar is going to have on her health. So she's going to allow herself a total of 3,000 calories. She's done some research and discovered that the cake contains 100 calories per slice and the lemonade contains 500 calories per litre. She's written another equation. 3,000 equals 100x plus 500y, where x is the amount of cake and y is the amount of lemonade. Beatrix now has a system of linear equations, which she knows how to solve. She multiplies the first equation by 50 throughout, so that the x term is identical in both equations. Then she subtracts the first equation from the second, which eliminates the x term altogether. She could have subtracted the second equation from the first, but she realised she'll have fewer negative numbers to deal with if she does it this way around. She now has an equation with only one variable, y. With a little rearrangement, she finds that y is equal to 4.29. Now she substitutes the value of y back into the first equation, and with a little more rearranging, she arrives at a value for x. That's 8.56 slices of cake and 4.29 litres of lemonade. Clever girl. Let's attempt to visualise these data with geometric vectors. The data about the cake is one vector. Let's call it C for cake. And the data about the lemonade is another. We'll call it L. At a glance, it's apparent that lemonade will give you more calories for your money. If calories didn't matter, then the only limitation on what Beatrix could buy would be the amount of money she has to spend. And you can see there are, theoretically, infinite possibilities between all cake and no lemonade, and all lemonade and no cake. That is, infinite linear combinations that satisfy her first equation. However, with a limitation of 3,000 calories, there is only one point at which calories and cost intersect. There is only one solution to this system of linear equations. And Beatrix found it by decomposing a linear combination of C and L. One final thing you might like to consider. Suppose that Beatrix is determined to carry home exactly 5 kilograms worth of goodies. She could come up with a third equation, expressing the total weight she wants to carry in terms of the weight of a slice of cake and the weight of a litre of lemonade. She would then have 3 equations with 2 unknowns. Unless the amount of cake and lemonade that she's already calculated just happen to weigh 5 kilograms, she's not going to find a solution. 3 equations with 3 unknowns, well, we've already seen that's a problem she can solve. Maybe Beatrix should consider throwing some lollipops into the mix. By the way, one day Beatrix will grow up to be an aerospace engineer, and she'll use the same techniques to select materials for a new type of jet.